Okay, hello. Welcome to our OneClass channel. My name is Joey. I'm going to be your chemistry teacher for this session. So, throughout this kind of past couple of weeks, we've been going through a session of verifying solutions for frequently asked problems in chemistry and in mathematics. Both of these subjects are taught in the secondary level as well as also in the university level. So, we've been going through this kind of journey of verifying solutions by teachers such as myself, and we've been kind of teaching you concepts through these problems as well. So we're going to continue this kind of process for chemistry, and I have a set of questions for us ranging probably in about the senior level chemistry. So what you would typically find in a grade 12 classroom. Again, my name is Joey. I'm currently a secondary school educator in Ontario, and my teachable subjects are chemistry as well. So without further ado, let's get started on these problems for today. And I have about 10 problems for you for this live stream here. So let's get started. Okay, so my first problem here is it says here, identify acceptable names for the following molecule. And it's kind of hard to see these options. So let me rewrite this for you here. So number one here, I want to name this molecule, right? So I have some type of ring structure here, and bonded to a bromine and bonded to a bromine here, and then it says I'll check all of the names that apply. So all of these names I have here. So let me write this in. I guess I'll write this here. So I have P dibromobenzene, 4,6 dibromobenzene. And it basically all of these guys here are dibromobenzene. So let me just I'll write dibromobenzene once, and then all they're changing is the prefixes. So the next one here is 4,6 dibromobenzene, and then it's 2,4 O dibromobenzene, 1,3 dibromobenzene, 3,5, and finally M. And all of these guys are dibromobenzene. I just don't want to write them all out. So I can put these air quotes here. Just to say that they're all dibromobenzene here. So, we want to identify the acceptable names for this molecule. So let me do this in blue. And how do we name this structure? So obviously it's dibromobenzene, like all of these guys here. But how do I utilize these naming structures here? Like what is up with these numbers here? So in order for me to kind of figure this out, what I'm gonna have to do is I'm gonna have to start labeling the carbons, right? And if I want to label the carbons here, what I would have to do first is I can either choose to do the numbering system or the orthoparameta system. So there's two systems of naming here. So I have one here, which is IUPAC. I have one that's IUPAC. So again, I follow the numbered carbons, and then I would do the prefixes according to that. So that's this kind of systematic way. And then the second one would be more of a common name. So more of a common name, and this is more based on the positions in where they stand. Common names for positions. So let me do number one first. And number one here is IUPAC. So if I wanted to do IUPAC, I would just follow IUPAC guidelines if I were to name the structure here. So I'm going to say maybe I'm going to put carbon number one on this bromine here, or I could put it on this bromine here, and I would count either left to the right way. So in this case, because they're the same, I'm just going to I'll go clockwise for you. So this is carbon 1, carbon 2, 3, 4, 5, and 6, right? So if I were to use IUPAC, I would get one name, right? And I would get here, this would be, again, I have a bromine on 1 and a bromine on 3. So this is 1,3-dibromobenzene, which means this guy here, this name here is correct, right? 1,3-dibromobenzene. So this is an acceptable name for this molecule here. However, I can also have, so that was the IUPAC name. So we did the IUPAC name here. But we also want the common name for the positions, right? So if I were to look at this benzene here, and I can say here that if I were to look at this benzene from this approach here, where I'm saying this here is 1, this here is 2, 3, 4, 5, 6, and this is the relative positions and this is not, sorry, that's not relevant. It's kind of like a permanent position for benzene here. And we can use common names such as ortho, para, meta to figure out where the positions of these bromines are. So let me do that for you here. So usually with a molecule here, I would like to rewrite this. I want to redraw this molecule so that the carbon 1 is actually at the top. So let me redraw this here, and I will let me erase this guy here. And I'm going to redraw the structure. Again, this structure is the exact same thing. This is going to equal this guy here, right? I'm simply just reflecting this here. It's exactly the same structure here. Sorry, this line isn't that great. It's exactly the same structure here. So in this case here, my carbon 1 is always actually on this guy here, and then everything else is relative. So you can think of this as this is the ortho meta para naming kind of way. And if I were to say this here is carbon 1, and I would say these guys here, 1, 3 here, are meta to this carbon 1. So this here, these two positions here, or let me do this in black here. These carbons here, these guys are meta. So you can say this here is meta. I have, let's see, I have a 1, 2 position. So 1, 2 would be, actually, let me redraw this here. If I have a, if I'm using the same IUPAC naming here, my carbon is 1 is here, this is 2, and this is 3, right? In this case here, if it's a 1, 3 positioning here, this here is going to equal meta. If I had, for example, I'm going to write this in blue here, if I had a bromine that was not here, but if it was on the second carbon, this here is a 1, 2 position. So this here would be a 1, 2, and this would be a ortho position. So if it was right beside it, and then finally, if I had something that's polar, like totally opposite of this, so if I had, if it was on 1, 2, if it was on the fourth carbon, like so, and I'll do this in red here. If my BR was here, so totally opposite here, 1, 4 equals, this would be para to the bromine here. And in this case, we have a 1, 3 situation, right, going on here. So 1, 3 would be a meta dibromobenzene. So remember, this is here's 1, 2, and 3. 1, 3 are the bromines here. So I can say this here is a 1, 3 meta, or I can say it's meta dibromobenzene. So which means this solution is also correct. So I can say that if I were to identify the acceptable names, so therefore, so 1, 3 dibromobenzene, and I'll write this out, and M dibromobenzene are your acceptable names for this molecule here. So again, there's two kind of ways to kind of name these guys here. And one is using the IUPAC way, and the other is using the meta ortho para way. And this really helps us when we have like more than one. This kind of helps us identify kind of when we work with organic chemistry, when we look at, oh, it's meta directing, or it's para director, or ortho directors. And these are a lot easier for us to, it's easier to communicate in this than saying, oh, it's 1, 3, or it's 1, 4, it's 1, 2. So this is a better system when we talk about organic chemistry in the higher levels here. So the solution here is 1, 3 dibromobenzene and M dibromobenzene. And as you can see here, they labeled kind of the same thing here. So they have 1, 2, and 3 on these benzenes, which means it's M dibromobenzene, or it's 1, 3 dibromobenzene here. So this solution here is correct. It's a good analysis as well. Okay, let's do number 2. 2 is asking us to determine the pH of each solution. So I have 2 solutions here. So I want the pH of each solution. So the pH of 0.17 CH3 NH3I. And then I want the pH of 0.25 Ki. Okay. So if I have this, I'm going to do, this is a 2-part question. So I'm going to do the first part here. So this is, I guess this is part A, you can say. And this part is asking us the pH of 0.17 CH3NH3I. So if we want to find the pH of this, I would have to actually break this guy first down, right? So I have CH3NH3I. This is going to dissociate into water, right? This is going to dissociate in water. Or it's going to ionize, sorry, not dissociate. It's going to ionize to form CH3NH3 plus this would be I minus, right? Plus our iodine here. And this here, and we don't really, this step isn't in equilibrium, but we care about this this CH3NH3, this methylamine cation here. So this guy is going to then react with water, and that's going to give us our equilibrium kind of reaction here. Plus H2O. It's going to give us what we have here is this H is going to be given to this H2O. So I have H3O plus again CH3 and H. Now it's 2 here, and these are all. This is all an aqueous solution. So if I were to write the states, I could write the states as well. AQ, and this is AQ as well. So basically here I have my again methylamine. If I'm writing my equilibrium equation here, it's going to form my hydronium ion, and then I'm going to form my CH3NH2 here. My this here is the methylamine. So what I'm going to have to do is, again, I'm looking at my concentration here. I have 0.17 here, right? So if I have 0.17 molars, you can assume that I have, again, this is here was 0.17. This here could also be 0.17, which means if I did my ice table, this here is also 0.17 here. So my concentration of this cation here is 0.17 molars. And what we can do now is we need to find our KB of this solution here in order for us to solve for this equation here. So as you can see from the solution here, what we have here is they're doing an ice table like so, and they actually found a KB from databases. So let me just search it up and see if this KB is correct here. So give me a second here. So I'm gonna type in PKB of this is CH3NH3NH. NH2 here, and this is 3.3. I'm getting 3.36 or 3.32 here. Sorry, just give me a second. So I want to double check if that's right here. We're saying it's 3.35, so it's about 3.36. Okay, so I'll take 3.36 as our PKB here. So I'm going to use this as well. So if I did an ice table, so let's put my ice table here. I can say that I'm starting with 0.17. The water does not matter in my equilibrium equation, and I started with 0 hydroniums and 0 of the CH3NH2, right? I'm going to minus some type of x. I'm going to add x and add x here, which means that in equilibrium I have 0.17 minus x here, and have x here. So now what we can do is we can write our expression, right? And before we write our expression here, I'm going to assume that this PKB here is right. So this PKB is going to be of our CH3NH2, and this here is going to equal 3.36. So if I want to solve for the KB expression, all I'm going to have to do is I can follow this equation here. And let me do this in black actually, because it's not part of my ice table anymore. So my PKB here is 3.36. Then my KB is simply just 10 to the power of my negative KB here, which is 10 to the negative 3.36, which will equal, let me take out my calculator here, 10 to the negative 3.36, which will give me 4.37 times 10 to the negative 4. So as stated here, which is great. 4.37 times 10 to the negative 4. This is our KB here. And now what we can do is we can write our equilibrium expression, right? I have my KB, and then I also have my concentrations here. So KB, I know it's going to equal the concentration of my hydronium times our concentration of our methylamine divided by our reactants here, which is the CH3 and H3 plus. And then, given this, I know that my concentrations of hydronium is X here. This guy is also X. And then, as found in my ice table, this here is 0.17 minus X, right? So 0.17 minus X would be the concentration of my CH3NH3. And my Kb here is simply just, my Kb here, I actually, I can't use my Kb here in this case because I'm actually making my hydronium ion, right? So I'm actually gonna have to find my Ka of this guy here. So this is actually a Ka expression, not a Kb expression here. So in order for me to find my Ka, I'm gonna have to relate it to Kw. So this is some side work here before we actually plug it into this guy here. So I know that Kw equals Ka times Kb, and Kw here is 1.0 times 10 to the negative 14 equals Ka times 4.37 times 10 to the negative 4, which means Ka here is going to equal, I'm simply just dividing 1 times 10 to the negative 14 divided by 4.374 here. So do that on my calculator. I'm going to get a value of 2.29 times 10 to the negative 11. And this here is actually going to be my Ka expression here. And as you can see, they did the exact same thing for Ka here, which is great. So I can say that my Ka here is 2.29 times 10 to the negative 11. 10 to the negative 11. And the reason why we have to use Ka and not the Kb here is because we're making hydronium ions, right? If we make hydronium ions here, we need to get our Ka of this expression here. So that's why I can't use Kb. If I use if it made hydroxide ions, what I can do is I can use the Kb here. But because I'm using making hydronium ions here, I'm forced to use the Ka here. So again, this here is my Ka expression. I'm going to use a small x approximation to get rid of this minus x here. I'm going to multiply both sides by 0.17. Times 0.17, I'm going to get a value of, this is 3.89 times 10 to the negative 12. And then I'm multiplying the x's here. I can square root both sides to get me, well, x here would be 1.97 times 10 to the negative 6. And this here will be my concentration of my hydronium ions, right? This guy here is going to equal H3O plus, like as I said in my ice table. And then now I can finally find the pH, right? And the pH here is simply just negative log of higher hydronium ions. And this pH will now equal negative log of this guy here, 1.97 times 10 to the negative 6 moles. This here is a mole, sorry. And this here is going to equal simply just the calculator, negative log times 1.97 times 10 to the negative 6. And this will give us 5.71. So our pH of the first solution here is 5.71, and this here is our answer for 3A. And as you can see, this guy should be 5.71 here, yes. So pH here is 5.71, which is great. So this first solution here is correct. And finally for part B here, part B is different, right? I have a solution of pH of 0.1725 molars of Ki. I forgot the M here. This here is a molarity of Ki here. So let me write that down as well, of Ki. So this here is part B. So we solve for part A, which is 5.71, which is great. And part B is now asking us, we wanted 0.25 molars of potassium iodide here. And this here is an ionic substance, right? Ki here is an ionic substance, and I believe it's going to be a strong acid here. And the reason why I know this is because Ki here, it's going to dissociate into our K plus ion plus our I minus ion, right? And this here, and as I'm pretty sure, yes, they dissolves completely, right? Because it's an ionic substance for Ki. And then my Hi here is going to then solve and then react with my water, right? This iodine is going to react with my water, and then I'm going to form, again, this here would be Hi plus OH minus here. And this here is actually this here is not in equilibrium because Hi here is a strong acid, right? This guy here is a strong acid. So therefore, if I don't have an equilibrium constant here, if I don't have an equilibrium solution, all I'm going to do is I'm simply just using my mole table, right? And if I'm assuming it's a constant concentration or a constant volume here, this is 0.25 molars, which means this guy is 0.25 molars, which is 0.25 molars, which means HI has to be also 0.25 molars here. So all I can do is all I'm doing here is I'm simply just using this here is my strong acid here. So again, Ki here is dissolving into I minus here, and then I minus then reacts with the water here. So Ki here is actually a salt, right? This guy here is a salt. It's an ionic salt produced by a strong base and a strong acid. And let me write down like an equation here. Let me erase this here because we actually don't have to do any math here. This is just some side work here. But if I'm producing potassium iodine and water in a neutralization reaction, I can assume that my K here is going to be my metal for my base here. I can think of this as maybe potassium hydroxide, and HI would be my acid here. So it's a product of these two guys. It's a double displacement reaction, neutralization reaction, and I have hydroiodic acid plus potassium hydroxide would give me my potassium iodide here. And both these guys here I know are strong bases and strong acids, and you can, this here is a strong acid, strong base. So therefore, if I have a strong acid, strong base neutralization, it's going to neutralize, which means like the Ki, the pH of the salt here is going to equal the pH of Ki here is going to equal 7 because it is a strong acid, strong base reaction here. So my ionic salt is neutral in this case. So again, this solution here is correct. You could think of this guy as also kind of like, you can think of this as also like this equation here. Again, I have this HI here and this OH is going to neutralize, right? I have a strong acid here and a strong base here. Both of these guys will neutralize to form a neutral compound as well. So this solution here is correct. It's a good analysis as well. Again, these questions take much longer just because there's again two kind of questions in one, and a lot of these buffer or acid-base equilibrium questions, not buffer, but acid-base equilibrium questions do take a long time just so I can explain everything as needed here. Okay, so question 3 says classify each statement about effective nuclear charge ZEF as true or false. Okay. So I care about effective nuclear charge, and it says here I have all of these guys here. So let me read the statements here. So it says, in a beryllium atom, a 1s electron has a greater ZF than a 2s electron. So across a period, as ZF increases, atomic size decreases. Electrons in a p orbital are more effective than those in other orbitals at shielding other electrons from the nuclear charge. A 1s electron in beryllium atom has a smaller ZF than a 1s electron in lithium. And finally, the second last one here is effective nuclear charge decreases from left to right across a periodic table, across a period on the periodic table, and effective nuclear charge is dependent on the number of electrons present in the atom. So we have a lot of statements here, and what we're doing here is we care about this concept of effective nuclear charge, right? So let me write this down here. Effective nuclear charge. And what we're doing here is with our effective nuclear charge here, what is effective nuclear charge here? So you can think of this as the net positive charge experienced by an electron in a multi-electron atom, right? So if you had something that's not hydrogen, or something that, for example, beryllium, if you have a beryllium atom, you have your Be is here, you have your first shell is filled with 1, 2, and your second shell is 1, and then also 2, right? Again, these are very, very bad diagrams. Let me redraw this as a nicer diagram here. Okay, so you can think of this as my beryllium atom. In my first shell, I have 2 electrons, and then in my second shell, I also have 2 electrons, right? So what is effective nuclear charge? Again, it's this net positive experienced by electrons in a multi-electron atom, right? So you can think of this as You can think of this as also the same as our shielding effect, right? So again, we have here these guys here are net positive. So again, in the nucleus here it's net positive, and these electrons here are negative, right? Sorry, this here is negative, this is negative and negative. And the effective nuclear charge, or the shielding effect here, is if I'm looking at these two electrons specifically, so one in the 1s and one in the 2s kind of orbital here, these guys are going to repel, right? Both of these negative electrons don't like each other. They're only attracted to this nucleus here. So you can actually calculate ZF actually through this concept, right? So you can say that ZF here is going to equal Z, which is the number of protons in the nucleus, so minus S, which is the number of electrons between the nucleus and the electron in question, so the number of non-valence electrons. In this case here, I have two non-valence electrons, right? So S here equals 2, so I have Z minus 2, and then Z here is our, again, number of protons in our beryllium. And beryllium we know here as, I believe, 4 protons, right? So again, I believe it's my fourth element here, so this here is 4. So you can think of ZF here as 4 minus 2, which would equal 2. And as you can see, what we're doing here is, as we are increasing the number of electrons, increasing the number of protons in our element here, as we go from kind of left to right on a effective nuclear charge, it's going to increase, right? Because the number of electrons here, Z value here, is going to increase. So therefore, it's going to increase from left to right. So this, I can say here that this guy is going to be false here. Let me just let me look at the solution for you, so you can double check the solution here. So it says here decreases from left to right here would be, let's see. Yes, so it's going to be false, right? So again, effective nuclear charge decreases from left to right. It's actually going to increase across a period, right? Because remember, if I'm increasing my number of protons here, the Z, my ZF will also increase here. So this solution here, this one here is correct. Let me read from up to down here. It says, in a beryllium atom, the 1s electron has a greater ZF than a 2s electron here. So 1s I would be focused on this guy here. This guy would be the 1s electron, and this here is a 2s electron. So this here is a 2s. This guy would be the 1s here. And which one would have a greater ZF? Well, in this case here, 1s would have a greater effective nuclear charge because it has less number of non-valence electrons, right? In this case, it would be simply just itself here, and 2s1 I would have two non-valence electrons here. So again, the 1s, the effective nuclear charge for the 1s electron is indeed greater than the 2s here. So I believe then this one here would be false, I believe. Oh no, this here is 1s beryllium and 1s lithium. Sorry, so that's not it. That's a different question here. So this one is correct. Electrons in a p orbital are more effective than those in other orbitals at shielding other electrons from the nuclear charge. So it's asking, so it's talking about specifically electrons in the p orbital here. Are they more effective than those in other orbitals at shielding other electrons from nuclear charge? In this case, it's actually false, right? And this solution here is correct because I also have d and f orbitals as well that we did not consider because we don't have enough electrons in this case. These guys are also participate in shielding effect as well, right? So you have obviously the s orbitals are going to, like these guys here are going to shield away. They're going to shield kind of from this 2s electron from this nucleus here. But also, if I were to add again p orbitals and d orbitals as well, they can also participate. P orbitals can also participate at shielding as well. And with s orbitals as well, with s electrons. Sorry. So this here is also false. So this solution here, this statement here is true, or is correct. Sorry. We talked about this statement already, so I'll move down to these guys here. So across a period, effective nuclear charge increases, atomic size decreases. That's true, right? So we talked about atomic radius. It decreases as a down a group, and it increases across a period, right? So this here is true. And we said already effective nuclear charge increases here, right? And then this guy here, I'm going to draw this out for you because I'm going to draw the lithium as well. says here, one s electron in a beryllium atom has a smaller ZF than a 1s in a lithium. So I'm going to write lithium here just to visualize this for you. So this Li, I have 1 electron 2, and then I have 1 in the one valence electron here. So again, here it's asking us 1s is smaller ZF than a 1s in a lithium. So this guy here, I care about, let me do this in red. I care about this electron here and also this electron here. This is also the 1s in lithium here. And this one, because my atomic number of beryllium is higher than my lithium here, it's going to, the ZF is higher, right? Like we said before. So I can calculate the ZF for this electron here. It's going to equal the number of electrons or number of protons, which is 3, right? The 3 is lithium. And then minus 2, right? Because I have 2 non-valence electrons, 1 and 2 here. And this here will give me 1. And because 2 here is greater than 1, then beryllium here will be my higher, has a greater ZF here than lithium here. So it's actually, this word should be bigger for this statement to be true. So false here is correct. And finally, effective nuclear charge is dependent on the number of electrons present in the atom. That's true, right? And that's this S value here. This S value is the number of non-valence electrons in my atom here. So this solution here is correct. Good analysis as well. Okay, number 4. Asking us, ammonia NH3 is a weak base with a Kb of 1.8 times 10 to the negative 5. What is the pH of a 0.33 ammonia solution? Okay, so let's answer 1. So this is a 2-part question here. So I have a Kb of 1.8 times 10 to the negative 5. And I want the pH of a 0.33 molar ammonia solution. Okay. So let's look at the solution here. I can write my my equilibrium equation down. Right? I have NH3 plus H2O. It's going to be in equilibrium with NH4 plus OH minus. Right. So again, this hydrogen is going to be. I'm going to give this hydrogen to the ammonia atom here to become ammonium, and I get OH minus here. And then I already know the Kb of this one here. So because I'm producing hydroxide, I want my Kb, which is good. So I have 0.33 molars here. And then what I'm going to do is, again, I'm going to do my ice table. Again, I don't care about the water here. I start with 0, and then I start with 0 here. And what I'm going to do is I'm going to minus some type of concentration here. I will add X and add X. So in equilibrium, it's 0.33 minus X. I have X here and I have X here. What I can do now is write my equilibrium constant equation. So I have equilibrium, so I have Kb here. This is the equilibrium equation here. I have NH4 plus here, this is OH minus, divided by NH3 here. And this here, I know it's 1.8 times 10 to the negative 5, right? 1.8 times 10 to the negative 5. This will equal, again, X times X here, divided by 0.33 minus X. And then what I'm going to have here, I'm going to use my small x approximation to get rid of this X here. And I'm going to multiply both sides or by 0.33. So I have 1.8 times 10 to the negative 5 times 0.33. This will give me a value of 5.94 times 10 to the negative 6. This will equal X times X is X squared. I can square root both sides to get me X would equal 2.44 times 10 to the negative 3 here. This is our molarity. And what I can do now is I have this molarity here. This, I know it also equals my concentration of my hydroxide, right? So I can simply solve for now the POH before I solve for the pH here. So POH will give me, it equals negative log of the hydroxide ion here. POH equals negative log of this here is 2.44 times 10 to the negative 3 moles. Sorry, molarity here. POH will equal, I'm simply just putting that into my calculator. Negative log of this will give me 2.61. And then finally, what I can do with this guy here, POH, is I can relate this to pH, right? Because I know that pH plus POH equals 14, right? And if I know that pH plus POH, which is 2.61, equals 14, I can solve for my pH. pH is simply just equals 14 minus 2.61, which is going to be 11.39. So this here is my solution for 1A, and as you can see, this solution here is correct as well. They used half pKb minus log C. Personally, I actually don't like this equation. It doesn't really tell you anything about, it's not using an ice table, and I actually don't know where they derived this equation, to be honest. It might be a variation of Henderson-Hasselbalch. I'm not very sure, but the way I was taught it, I would use an ice table to solve for this problem here. So this solution, either way, both solutions are correct, that's good. And it's asking us, B here is what is the percent ionization? So B here is asking what is the percent of ionization of ammonia at this concentration. Express the percentage numerically to 3 significant figures here. So again, if I want to find the percentage of percent ionization of a weak base, because it's ammonia of a weak base here, what we can do is we can we know the equation here, right? So let me just find the equation for you. And usually you're given these kinds of equations for for these guys here. So let me just double check the equation for you, because I actually don't know it off the top of my head. Let's see, percent ionization. So I have there, this is H plus divided by HA times 100 here. So this would be percent for an acid here. So so this would be hydroxide. So this is the or actually in this case it would be hydroxide. Or no, this would be the concentration of our ammonium over ammonia. Yes. So NH4 plus divided by NH3 here times 100%. This will equal the concentration of ammonium is exactly the same concentration as a hydroxide, like I solved for, right? So this is 2.44 times 10 to the negative 3 here. So 2.44 times 10 to the negative 3 moles divided by concentration of ammonia was 0.33, right? And this here, and I'm going to multiply that by 100%, and this should give me a percentage. So 2.44 times 10 to the negative 3 divided by 0.33 times 100 will give me a percentage of, this is, this here would be 0.73%. And they got 7.38%. So they're, I think they're off by decimal places here, which is odd, but give me a second here. So again, it's percent ionized divided by, or the percent divided by the the ammonium divided by the ammonia. So let me see if they got the solution incorrect here, or if I did. Yeah, so I think here it's actually 0.738 here would be our solution, because again it's just the concentration of ammonium over ammonia as times 100 would be our formula for the percent ionization here. And yeah, this would give me 0.73%. So this here is my answer here, and they got 7.38. I think it's maybe some type of error here, because what they did was they had KB over C, which is, I don't know what C is here. I think C here would have been the concentration, and they took it, then they squared both of, so they square rooted both of these guys here. So I don't know where they got this kind of equation here, but 0.73 should be our solution here. So solution here is partly correct. A is correct with pH equals 11.39. However, percent ionization equals our HA equals, and I'll just write NH4 plus concentration of that divided by our concentration of NH3 times 100, which will give us 0.73%. So I'm going to say the solution here is incorrect, just because they got B here wrong. And let's look at the next question here. So this here was, what question was that? That was 3. This here is 4. I don't know why I wrote 1 here. This was 4. Let's look at 5 here. 5 is, what is the solubility of MOH2 in pure water? MOH has a KSP of, I believe that's 5.45 times 10 to the negative 18 here. I think just the formatting here is off. So I want the solubility of this. So KSP, or what the molar solubility is what I care about here. It's 5.45 times 10 to the negative 18. And again, what I'm gonna have to do first, I'm gonna have to write down my my chemical equation, right? So I have MOH here, or MOH2, sorry, is going to again dissociate into two things, right? Because again, it's gonna be soluble in water. OH is my hydroxide ions, so in this case, this is my anions, which means my M has to be a cation, right? So M here plus this is OH, 2 OH minuses, right? 2 OH minuses. And if I have 2 OH minuses, I'm going to have to balance this out, this charge here, which means this charge has to be a 2 plus charge here. So here is my solubility kind of equation. And what I can do here is I can solve for, again, the molar solubility, right? So what they're doing here is, again, they wrote this as S and 2S here, or you can write them as X's. It doesn't really matter. I personally write them as X's myself, so I'm going to use X's here. So, and again, we don't get a starting concentration here, so you can say that this here is simply just X, this here is X, and this is 2X here for 2 hydroxides here. And then what you can do is you can write your KSP equation here is going to equal our basically the product of these products, right? Sorry, the product of the products, which is kind of weird here. But this here's M2 plus times OH to the power of 2 here, because I remember my coefficient here is 2. I need to be able to reflect that in my KSP in my equilibrium equation here. This here is simply just X. This here is 2X squared. So simply what I'm going to have is X times 2X squared here is 4X squared, which is going to be, in total, X times this guy here is going to be 4X cubed here. And this will equal, again, my KSP. And all I'm going to have to do is simply, and because I'm given my KSP here, I can simply just solve for X, right? So I can plug in my KSP, which is 4.45 times 10 to the negative 18 equals 4X cubed. I can divide both sides by 4 here to give me a second, divide by 4 would give me, this here is 1.3625 times 10 to the negative 18 equals X cubed. And I can cube root both sides to get my answer here. In this case, X here is going to equal 1.11 times 10 to the negative 6. And this guy here is going to be our molar solubility for our solution. And as you can see, X here is our 1.1086 times 10 to the negative 6. I wrote 1.11 just to round it off to the nearest 100th place. So this solution here is correct. Again, they did the cube root and whatnot. I simply just used my calculator here, so it doesn't really matter. Usually you're given the calculator, so you don't have to do this tedious step here. It's actually probably impossible for you to do this by hand. So this here solution is correct, or it's not impossible, but very, very, very tedious here. So solution is correct. Great analysis. So 5. Number 6 is asking us, what is the electron configuration for a chloride ion? So electron configuration for chloride ion. So first let's write the chemical formula for a chloride ion, right? For chloride is chlorine, so it's Cl, and it's an ion, right? So if I look at my periodic table here, chlorine exists in my halogens, right? Cl here, and I want an ion here, which means I'm gonna add another electron here to make it Cl minus, so that it's isoelectric with argon here. So in this case, it's Cl minus 1, right? Or 1 minus, or just simply minus. So I want the electron configuration of this. So what I'm going to do is I'm going to start off my electron configuration. I'm going to have, let's see how many electrons are in chlorine here. It's going to be in, both my electrons are going to be in the 1s orbital for, so I'm going to write 1s2 for these two guys here. 2s2 would be the second line here, so I have 2s2 as well. 2p6 would cover all of these electrons, these six elements here, so, or 6 electrons. So this here is 2p6. I have 3s2, which is these 2 electrons here, so 3s2. And finally, I'm going to have 3p. I have 1, 2, 3, 4, 5 for chlorine, but remember, because it's an ion here, I'm going to add 1 more electron, so it's going to be 6, right? So this here would be 3p6. And this here is the electron configuration for the chloride ion here. So this is Cl minus, sorry. Cl minus is going to be 1s2, 2s2, 2p6, 3s2, and 3p6 here. And if you want me to draw the energy level diagram, I can also do that too. So think of 1s as, or let me actually use some lines here so it makes it actually a lot nicer for you all. So here is our energy here. So I'm going to start off with a 1s here. 1s is going to have both electrons here. And then I have our 2s, which is our, this shell is also filled. I have a 2p electrons here, which is also filled. I have 1, 2, 3, 4, 5, 5, and 6. And then I have 3s here, which will be 1 and 2. And finally, I have 3p shells, and this is also filled, right? 1, 2, 3, 4, 5, and 6. And this here is my energy level diagram for chlorine as well. So let's look at the solution. So this is, they did the atomic number here for chlorine here is 17. So that they did the actual electron configuration for chlorine first, and then they added 1 more electron to make it 3p6 here. So this solution here is correct. And again, I want the extra kind of way to draw the energy level diagram for you all as well. And 1s2, 2s2, 2p6, 3s2, 3p6 is therefore correct. So the solution is correct. Good analysis. So that was number 6. Let's look at 7. Maybe we do 2 more questions here for the day, depending on time here. I want the molar mass of benzene. So now we're kind of headed straight. We're kind of heading not towards kind of grade 12 material, but this is more so grade 11 material now. So it's molar mass of benzene. So what is the molar mass of benzene? Well, I'm gonna have to figure out my chemical formula for benzene first. So benzene, benzene is what it has here. It's if I were to draw out the structure here, benzene. So, and then I have it's bonded to a carbon each, right? The circle just means here again, the circle means it's resonance stabilized, so it's actually these double bonds are delocalized electrons that's jumping around here. So it's only bonded to 1 hydrogen, which means if I were to count the carbons, I have 6 carbons, so C6, and I have 6 hydrogens. So C6H6 is my kind of chemical formula for benzene. And what I have to do is I have to simply find the molar mass, right? So I can say that the molar mass, big M, of C6H6 is going to equal. So what is it going to equal? I have C6H6, right? Which means I have 6 carbon electrons. So I can say I have 6 it's not electrons. I have 6 carbons, and carbon is again this guy here, right? It's 12.011. So this is 12.01 grams per mole. So this here is going to be my the molar mass of carbon here. I have 6 plus times 6 of those guys, and then I'm going to have also 6 times this hydrogen, right? I have 6 hydrogens as well, right? So if you look at my periodic table here, again, hydrogen is 1.008, right? So hydrogen, I can say that this is 1.008 grams per mole. I'm going to do that math on the calculator. So I have 6 times 12.011 here, which is 72.066. 66 grams per mole. Plus, and then I have 6 times whatever this guy is, right? So 6 times here is 1.008, right? Which is 6.048 grams per mole. I can add both of these numbers up to get me my molar mass, or my total molar mass of this benzene, which is 78.114 grams per mole. And this here is the molar mass of my benzene here. So as you can see, let's see, this solution here is correct. They got 78.11. 114 is close enough. And again, all they're doing is they're simply taking the atomic mass of our carbon and our hydrogen, which is 12.011 and 1.008, and they're multiplying it by 6, right? So they did C6H6 is 12.01 times 6 because I have 6 carbons, plus 1.008 times 6 because I have 6 hydrogens, and it's going to, and they're going to sum it up to give me 78.114. Solution here is correct. It's good analysis as well. And let's see if I can do one more question. I think I can actually for number 8 here. So I'm going to do this is number 8, right? Do number 8 and we'll finish off this video with this question here. Again, it's another electron configuration question. So I want the electron configuration of Ag here. This is silver, right? Ag is silver. So I'm looking at my periodic table here. I'm looking for Ag. And Ag would belong to the transition metal section here. And as you can see, I'm scanning. Ag here is number 47, right? This is our Ag here. So I'm going to look at our the electron configuration for Ag. So if I were to write starting from the 1s kind of orbital here, Ag would be, let's see, 1s2, 2s2. So yeah, 1s2 for these 2 electrons here, 2s2 for these guys as well. I have 2p6, which is for this block here, 2p6. I have 3s2 for the next block. 3s2 is these 2 guys here, and then I have 3p6 is coming up next, right? 3p6 for those electrons as well. And then I'm going to have 4s2. These 2 are 4s2s. And then after 4s2, I have this entire block here. This block here is our D block. And we don't actually do 4D block. This is a 3D block here. So this is 3D10. So here is a 3D10 block. Because in my D orbitals, I can have 10 electrons. There's 10 orbitals. There's 10 electrons in total. So I'm going to write 3D10. And then these guys here are going to be my 4p6 orbital, 4p6, right? So this is 4p6. Kind of running out of room here. And then finally, I'm in my 5th row here, and this is what I care about, right? This is our 5s2 group. And then this here is my D block. And silver, as you can see, resides in my D block on the second last one, right? So you can count 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the 9th electron here. And this here, instead of my 3D10 block, this here is a 4D10 block. So this would be 4D9 for the 9th electron here. So it's 4D9. And this here is the electron configuration for silver. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then 4d9. So as you can see here, this solution here is correct. They wrote 1s2. They wrote basically the exact same thing as I did as well. So this solution here is correct. And this analysis is good as well. So solution here is correct. Good analysis. So that's all the videos. That's all the time I have for today. Again, thank you so much for tuning in. If you were in the chat, thank you so much. Again, my name is Joey. I stream basically every day, 5 days a week from Monday to Friday. I stream math on Monday, Wednesdays, and Fridays, and chemistry on Tuesdays and Thursdays. So you can come check me out there. If you like these videos, definitely give the OneClass YouTube channel a shout out. It's going to be youtube.com/OneClass. You can access all the live streams and all of the kind of uploads. We always upload our live streams on that YouTube channel as well. So you can definitely take a look. If you missed something or if you want to rewatch something as well, definitely take a look there as well. So again, thank you so much for watching. Stay safe, stay healthy. Have a great day. Take care.